Okay, so our next talk is from University of Maryland by Zeying on in-memory key value store live migration with NetMigrate. So over to you.
Thanks for the introduction. I'm Zeying, currently a fourth-year PhD student at Maryland. And this is a joint work with Yibo and my advisor, Professor Alan Daoxing Liu. So today I'm going to talk about NetMigrate, a network-accelerated in-memory key value store live migration serving. In-memory key value stores are widely used, such as for the features of machine learning, in-memory caching, and real-time analytics. And the data amount can be large. It can store billions of records and retrieve millions of them under the low latency constraints. In distributed key value store systems, data are sharded, and the sharding can be reconfigured over time. The live migration techniques here promises no service downtime during the key value store shard migration from one node to another, and thus it can meet the service level agreement. When we need to migrate the data, one popular case is for the load balancing. For example, there are two servers and the hot items A and B are both located in server 1. There are a lot of queries going to the server 1, and thus it's overloaded. If we can migrate part of the hot items to a colder server, then we can achieve the balanced load between them. Also, it can happen when users want to improve the spatial access locality, and also when there's a cluster horizontal scaling. Existing solutions of live migration of key value stores can be divided into 3 categories: the source-based migration, destination-based one, and hybrid one. Source-based migration uses the source node only to serve both read and write requests to key value pairs. However, when a write request arrives at the source, it can update an already migrated key value pair, and thus the source has the updated value, but destination has the stale value. So source-based migration protocol collects and sends the dirty data logs in source and sent to the destination. So the destination value will be updated. The benefits is that it can achieve the low query latency during migration because the source node already has all the query data. However, it incurs extra dirty data transfer, and also there's a downtime when terminating the migration because the source has to be frozen to avoid serving any write requests. Destination-based migration uses the destination server to serve all requests. However, a read request can access a not yet migrated data. The data is still in the source. So in the Rocksteady protocol, as a destination-based migration, it fetches the accessed data from source to the destination with on-demand pools, and then let the client retry the read request after a wait. And this leverages the data skewness so that the more likely accessed data is migrated to the destination earlier. It can have a quickly shift of source node's pressure, so it has a shorter migration time. However, it incurs high query latency and low query throughput during the migration because the data access is missed. It's not in the destination. For example, in the Rocksteady, it can increase the access latency by 100% to 400% compared with without the migration. The hybrid migration protocol can leverage both the source and destination server to solve the request during migration. And it's called hybrid because it bookkeeping the migration state somewhere. For example, in the fieldwide protocol, it keeps the migrated key ranges in the client library, but in every client library. It does the following. For write request, the client routes it to the destination, and all the updated value are in the destination. If a read request following access already migrated key, no problem, it will go to the destination and get the updated value. However, if a read access a not yet migrated data, the client library are not sure whether the key value pair is on the fly or stored in the source. So it issues the double read to query both backend source and destination servers, and then it merges the request with the latest version. Hybrid migration leverages both source and destination, so its performance is better when most of the data is in the source compared with the destination-based migration protocol. However, the double read mechanism here incurs large bandwidth overhead between clients and the servers, which is on average about 50%, because it lacks a fine-grained state tracking mechanism. So putting existing line migration system together in a 2D dimensional plane with x-axis as the migration time and the y-axis as the query performance, the destination-based Rocksteady has a short migration time but low query performance. But the source-based one has a long migration time but a good query performance. And hybrid Fuwa stands in the middle. We see that they suffer from trade-offs between query performance and migration time. Therefore, here we propose NetMigrate to achieve the three goals: minimal query performance impact, low extra overhead from the migration, and also acceptable and tunable migration time. Existing solutions fall short to do so because they don't know where the data is, and they pay the cost of going to the wrong places to fetch the latest value. And here, our key idea is to use the network as the indexing services and tracking the migration states. We use the programmable top-of-rack switches to track migration states because it has a centralized view of all the data movement under the rack, and thus it has the real-time information of who owns the data. Also, it serves as a gateway of communicating with other racks. For example, when there's a query coming from clients to the top-of-rack switches, and it will look up the migration state stored in the data plane. And then it can decide whether the query should go to the source or should go to the destination based on the current information of where the latest value is. The key enabler behind is the flexible programmability of the switch. It can parse, read, and update custom fields of the packets, and we can custom the packets at long rate. And also it has registers that can store the data. Here we use the registers to store the migration states. However, there are several design challenges behind. The first is, how can we track the fine-grained migration states given the on-switch resources are limited? And second is, how can we query during migration based on the migration states while maintaining the data consistency? So let's look at the first one. On-switch resources are limited. For example, it may have only 64 megabytes SRAM, while the migration key value pairs under the rack can be millions of. So our idea is to shrink the record granularity so that we record less migration entries to suitable for the limited switch resources. The key value source usually has a data structure hash table, and we track the migration not in the per key level. We group the consecutive several entries in the hash table as a group, and we track the migration state in the group level. And the rationale behind is it has the common prefix hash values. So given the definition of group, we define the data location of the group states. For example, suppose this group has 4 items, and at the beginning, all of them are in the source, so this group is not migrated. And then when part of them are migrated on the fly, the group is ongoing migration. And finally, when all the data items are moved to the destination, this group, we call it migrated. And then we still need to shrink the space. We propose to use the space compact probabilistic data structure, the Bloom filters and counting Bloom filters to track the data ownership. We use counting Bloom filters to track ongoing migration groups because counting Bloom filters the value can be dynamic, can increase and decrease. And we use Bloom filter to track the already migrated groups because once it's set to 1, there's no false negatives. And from not migrated to the ongoing migration states, the CBF is increased by 1, indicating this group is ongoing migration. And from ongoing to the migrated one, the CBF is cleared by -1, and BF is set to 1, indicating the group has finished migration. So here are a step-by-step example. We have this group, for example, to migrate. And at the beginning, the BF, CBF in the switch are all set to 0. And this indicates the group is in not starting migration state. And when something starts migration, the switch gets notified by a control packet sent from the source to the switch, and it updates the CBF accordingly. And finally, when the group finished the migration, the destination will send a control packet to switch, notifying that this group finished, and the CBF and the BF updates. So based on the track the fine-grained migration states, how can we query during the migration while maintaining the strong data consistency? So let's look at the first. Let's look at an inconsistent example. If the switch decides a write request is routed to the destination, and then the following read request, if it's routed to the destination, it can access the latest value. However, if the switch decides this read is routed to the source, it will access the stale value, and thus the result is inconsistent. So here, the key is to know where the latest data is. And here's an example in each group situation, how the switch routes the query. So when the BF and the CBF are all 0, indicating the group is not starting migration, the switch decides routes both read and write to the source. And similarly, when BF is 0, BF is 1 and CBF is 0, switch thinks the entire group has finished the migration and the data are all in the destination. The clients will, the switch will route both queries to the destination. And when this situation indicates the group is ongoing migration, part data are in the source and part data are in the destination, switch is actually don't know the accessed key is in the source or destination. So we do the following. For the write, we just write to the destination. And then for the following read request, we let the switch mirror the query packets and send to both source and destination. So one of them will return the latest value. And thus this double read maintains the data consistency. However, unlike the hybrid migration protocol FUA, which gives double read along all the time during the migration, the overhead caused by our double read is negligible because the period that a group is ongoing migration is short. Thus, this situation happens very less often. However, the BF, CBF, these probabilistic data structures can have false positives. For example, these BF entries are updated due to the hot collision, which meaning this group is actually not migrated. But the switch decides to route the read request to the destination, and it can access a not yet migrated data, maybe still in the source. So NetMigrate used the similar on-demand pool to fetch the data from source first to the destination and let clients retry. However, the overhead from this false positive situation is also negligible because the false positive rate is bounded by the Bloom filter theory. So putting it together, we have a top-of-rack switch data plan that use the registers to store the migration states and representing the probabilistic data structures, Bloom filters, and counting Bloom filters. And we use the switch controller to register for migration instance table basically mapping a source server to the destination server with their corresponding IP addresses. And also the switch decides the routing decision of different kinds of query packets. So leveraging both of them and carefully design a query protocol that guarantee the consistency, the overhead caused by the false positives and unsure states as the corner cases is small. And here we evaluate the net migration system with 3 commodity servers representing a client, a source node, and a destination node. And all of them are connected with an Intel to Fino switch. And we compare NetMigrate with the 3 kind of baselines. And also all of them are migrating a 16 gigabytes key value pairs from the source to the destination. The query workload is YSSB with different write ratios. And we can also limit the source server's budget to mimic that the source is overloaded and there's a load imbalancing scenario. And for brevity, we just show the comparison with source-based migration protocol and 5% write ratio query YSSB workloads. So let's look at the throughput. During the migration, we see that the source-based migration has a slightly lower throughput compared with without migration. And this is because the source nodes are experiencing the pressure from migrating data. And the NetMigrate, on average, will have a even higher throughput compared with without migration. And we see there's a performance peak because before the peak, the source and the destination, both of them can contribute to the query throughput. And after that, more and more data are migrated to the destination. And then the destination node is experiencing data ingestion from the migration, and also it needs to solve more requests. So the throughput drops. So compared with the 3 baselines, we can limit NetMigrate to have the similar migration time with them for fair comparison. And NetMigrate can have up to 78% average throughput improvement. Next, let's look at the medium latency. Source has a higher medium latency compared with without migration because the queries and migrations are queuing up in the processing queue of the backend storage. And however, NetMigrate can offer even a lower medium latency compared with without migration. This is because the source and destination, they share the query pressure. So still compared with 3 baselines, NetMigrate can have up to 65 average medium latency reduction. And for tail latency, it can have up to 39% reduction. And finally, let's look at the network overhead of different migration protocols. For destination-based Rocksteady, it only has the, so we decide the network overhead as the 2 parts, the extra network bandwidth used between the clients and servers or used between the servers. So destination-based Rocksteady only has the client-side extra bandwidth usage because the clients need to retry the query packets when the query is accessed on not yet migrated data. And source only has the server-side overhead, which is proportional to the write ratio, because the data log size is proportional to the write ratio. And Fuel on average has 50% client-side overhead due to the double rate between clients and the servers. And finally, the NetMigrate has both client-side and server-side overhead, but both of them are negligible. So in conclusion, existing key-value store line migration systems still suffer from low query solving performance and high overhead during the migration. We propose NetMigrate here, which is a network-based hybrid line migration approach, leveraging the programmable switch. It tracks the fine-grained migration states in the programmable data plan, and it can provide enhanced throughput and low migration overheads. Also, we open sourced the NetMigrate in this GitHub repo. Thank you, and I'm happy to take any questions.
Thanks. Have you, I don't know if it makes sense. Would it make sense if instead of a single top of rack switch maintain this state, if there were, let's say, a bunch of hosts with smart NICs or something like that? If this migration state is distributed across multiple places instead of just one, does it break anything, or it's just different?
Currently, it only works for all the backend storage are under the same rack, and we may extend by using multiple data planes at different racks, and we need to find maybe at least a common ancestor to for the clients to the rack to decide the current access key where it is.
Okay.
So yeah, it's kind of a current limitation.
Okay.
Hi, thanks for the nice talk. Quick technical question. You mentioned you used Bloom filters. Is that
Yes.
something that's supported natively on the Tofino, or can you build it on top of other primitives that are supported?
Oh, currently, so filters, the key components are just the hashing of something and update the value. So we build it using the register primitives. I know Tofino has some built-in Bloom filters, but that's seems for the communication between the control plane and the data plane. And here we purely provide the data plane Bloom filters.
Thanks.